It's 23rd of March, and we have reached class 19 in the UBC Ecosystem Modeling course called FISH 501. And I would like to welcome you to this class. And today I put up a picture showing UBC. It's for those it's mainly for those who are not at UBC. Oh, actually, none of us are really at UBC, but this is the campus, and you see Vancouver in the background. And this picture is taken north, looking east, and it shows Coast Salish territory. So we acknowledge that we are on the traditional, ancestral, and unceded territory of the Musqueam, the Tsleil-Waututh, and the Squamish people. I mentioned that before, but this is actually a shared territory between these three nations. The Squamish are mainly here south of Fraser River. This is the northern arm down the right corner. You see the locking brooms. That's the northern arm of the Fraser River, and that's mainly where Musqueam are. Tsleil-Waututh are in Burrard Inlet, all the way here up Indian Arm, so there's about 40 kilometers of water when you go in here. And the Squamish primary territory is in Howe Sound, which is just to north of here, so on the left of it. So this is the UBC campus. If you can see my arrow, this is the Institute of Ocean and Fisheries right here. And I'm actually speaking to you from home, which is over here on the right. And so much about this area. I mentioned that it's a Coast Salish territory, and would also like to mention that the recordings are available at the Ecopath YouTube channel and on the Facebook page, and that there is a Slack workspace that you can get access to if you don't have already by sending an email to me. And again, the course website is a Google website, and you can find it at this address here. And if there are any questions or anything, feel free to send me an email. Great. So much for this. Let's get on to the next part of it. That is what's going to happen today. We're going to start off with an broad overview about how we handle uncertainty in EWE. Santiago, sorry, it's actually Jeroen who's going to step in a few times there and bring us along for some of the things that he's been developing. And Jeroen is also going to be talking on Thursday about it's a leading question.
About the source code of Ecopath.
And
what you can do with it, and why it's fun. It's really informative.
So and a few other things while he's at it. Okay, and we are also going to briefly mention a tutorial about Monte Carlo sampling, and a few other things related to. Let's see how far we get with that. It's a pretty heavy program for today. The topic for today is handling uncertainty in Ecopath and Ecosim and Ecospace to some extent as well. And this can only be a very brief overview that we can give here in this short time. I think the main thing you have to think about when we're talking, the main thing I want to mention when we're talking about uncertainty is that you have to remember your research question. Once again, your research question tops the list of what has to be considered. You want to look at uncertainty at that question, at that level. It's not possible. It's even absolutely uninteresting, boring to address the question of uncertainty overall. Let me illustrate that by mentioning that Fulton once calculated, based on the parameter settings in Atlantis, if she was to look at sensitivity which is an aspect of uncertainty, how sensitive is the output to the input parameters. If she was going to address that question by varying the parameters in Atlantis, it would take more than the collected computing power of the, maybe it was the biggest supercomputer on Earth. It would take them it as long as the life of the universe to make that calculation. It's almost like the 42 I've been talking about a few times, where the Earth was a supercomputer. Maybe they could have done it in a few light years, or who knows how long time it would take. Light years a distance, but you just can't do it. You cannot look at the entire uncertainty complex. It's impossible. And it's not interesting. That's a pretty important conclusion to reach there. So when we're talking about uncertainty, there are various kinds of uncertainty. And what I have here is something that comes out of Carl Walter's Adaptive Management book, which you should have access to in the shared folder with EWE related publications. It's not about EWE, but it certainly sets a lot of the stage for it. It's a fantastic book. You can build a whole career on that. Take that book and your clock code detective, you have the material for some really interesting things, and it forms the foundation for much of what we're doing in fisheries research today. When we're talking about uncertainty, there can be background variation or noise, which just give random, uncorrelated variation over time. Then there's parameter uncertainty, which is mainly what we're talking about here in the next half hour. There's also structural uncertainty. How well does the model describe the system? You can address this by having multiple versions of the model or different models, which we often prefer to do, to address a question. There's observation error, which includes sampling area and leads to uncertainty in biomass estimates. And finally, there's implementation error, which is the foundation for management strategy evaluation, which we'll also be talking about later. So there are a number of different kinds of uncertainty. That's the main thing I want to get through with this slide here. Okay, another and related question is model complexity. Again, on the left here you see a graph from Carl Walter's 86 book about adaptive management, indicating as you have more parameters, as you make the model more complex, there is prediction error variance goes down, but elements of parameter uncertainty increases. When you multiply these two together, you get an overall variance for the policy parameter, which indicates there may be a sweet spot, an intermediate complexity that we should be looking for. So this relates to the structural uncertainty about how we define our models. Christensen has a similar plot over here, how effective models are based on their articulation or complexity, two sides of the same coin. There is this intermediate spot, because they call it effectiveness frontier, an intermediate area, or intermediate complexity is a better word for it, and it's really useful to have that in mind when you are thinking about the structural complexity, how your model describes the system. As you make the model more complex, it does not mean the model gets better and better. This relationship breaks down after a while, and the more complex models just don't behave as well. There is this intermediate spot of complexity, and that's what we're searching for. That brings us to Monte Carlo methods. And Monte Carlo methods are really important for addressing parameter uncertainty. The foundation, I'll just get something up here. The foundation for that goes back to development of nuclear weapons after the war down in the Los Alamos National Laboratory. And the name Monte Carlo refers actually to the Monte Carlo casino in Monaco. It has, what is it? It's a way of using random samples to evaluate something. It can be uncertainty, or it can be to estimate things. If we look at the estimate things, the example we have over there on the right here illustrates how you estimate pi. If we remember, the pi can be estimated as the area that's inside here relative to the square area of the square. You can get from that into describing or to estimating pi. And just by dumping random samples here, see more and more, you can see up on the top how it estimates pi. And you can see you can actually estimate pi pretty well just by putting random samples in. Dropping random points on a map like this can give you an estimate for it. So Monte Carlo methods are useful for providing confidence intervals. That's what we can look for. Based on this, how good do we estimate pi, for instance? They do not address structural uncertainty. That's why you need the multiple models. But Monte Carlo methods are useful for addressing uncertainty. And they're also useful for estimating things like how do we estimate the area of this shape. You can see the equation down there on the bottom of the screen. And really, a Monte Carlo routine would be much easier. And dropping same way as before, we can get to how do we estimate the area of this size here, of this shape here, with uncertainty on it. So, a nice thing about Monte Carlo sampling is that even if we don't know the equation here, we can still estimate properties of that distribution that it comes from, just from random sampling. We can, for instance, look at what's the average in getting a sample means, even if we don't know the underlying distribution. It's one aspect of this. And it's much easier to calculate, as you saw in the Batman example just before. It was easy enough with the pi, but in the Batman example, I wouldn't want to go there. Now you can learn more about other courses about Markov chain Monte Carlo, which we have an implementation of in EWE. It's a Bayesian approach that uses random samples to generate new random sample. So we start and we, for instance, generate a number of possible Ecopath models. And then we sample from those, and by doing that resample, each sample actually depends only on what it was drawn from. That's this Markov property. And the more steps you put into such a Markov chain, the more the original unknown distribution gets to resemble, this outcome gets to resemble the original distribution. So they're pretty smart in this context here. But this area is a topic for a much longer discussion. I won't go there I won't dig any further into this. With regards to parameter uncertainty, we can look at that with regards to Ecopath input. But where it really becomes interesting is when we get to, remember where I started, what's the research question? And that relates to research and management question. And to address those what-if questions or other research questions, many of the research questions calls for using dynamic models. So that's where it gets interesting. We had in previous versions of EWE something we called the Echo Ranger, which would go in and to evaluate sensitivity of Ecopath parameters. So it was a routine that would go in, and it would vary the biomass, the PB, the QB for each group in the model, and then look at an EE2. What would if you varied this parameter, what would impact would that have on other parameters? So you varied the biomass and you looked at what indications it had. And it produced tables and tables and tables. And it was, to me, a very good example of it wasn't really interesting because there was no research question associated with it. It was just producing a lot of tables, and it was, yeah, you could use it to find parameters that had a lot of impact on other things in the model. We haven't carried this one over to the new version. We haven't done it because it wasn't really interesting, and because we had to prioritize. We always have to prioritize. We don't have any core funding for developing this, so we always have to prioritize what's most interesting to what should we concentrate on, what is the most critical part. And the Echo Ranger never made the cut for being brought over, because there are other ways of addressing things like sensitivity, and that's basically what we'll be talking about here. Another thing that we haven't brought over is this auto mass balance routine that was developed by Pat Kavanagh years ago, which in principle was very smart. I talked about it in the previous class, but very briefly, what that routine would do would be you gave it the input parameters, and then it would very elegantly and smartly find out what was a possible model to come out in the other end. But the few early uses of it were not really interesting, because you have to get beyond the point of you have to identify the errors that may be in the model before it makes sense. You saw when you were doing some of the tutorials, you've seen there, hopefully, what happens when you make a conversion error. You end up with biomasses or some other parameters that are totally out of line with reality. If you drop that into a model and you ask it to balance the model and find a balanced model, it's likely to produce garbage output, garbage in, garbage out. This is one area where that's the case if you don't identify those conversion errors that may be in a system. So, with regards to parameter uncertainty, there's a really smart way of addressing this, which is called Pedigree. I have mentioned Pedigree before when we started off, but again, Pedigree indicates how well a model is rooted in local data. I can't remember if I mentioned this in earlier class, but if not, let me just mention it. When we set up these Monte Carlo routines originally for looking at uncertainty, we had a workshop in South Africa where a group of modelers that had been working on southern Venezuela for years sat down, and then they looked through the model, somewhat like you see here on the left. For each group of them, they mentioned, so what do we know about biomass in this area? How much has it varied? Okay, what do we know about mortality rates, and how much have they varied? And what about consumption rates? And diets, how certain are the diets for this species? And they particularly said for this group of very experienced researchers, ecologists, they were able to go through the whole model and discuss this. And they actually had a lot of data about it, because they have been studying the Venezuela system very, very thoroughly for years. Now that's the only group that I've seen that have been able to sit down and actually make qualified estimates for parameter uncertainty for a whole model. So that's kind of an issue. How do we get uncertainty in when you have to have that kind of overview to do it like point by point? And the approach we're taking is this Pedigree one, where we're saying we associate uncertainty to what kind of information we have for that model. So if, for instance, as you see down here at the bottom right, if for the biomass it was estimated by Ecopath, then we associate confidence intervals with it. We say it has a very low pedigree. It has no root in local data. And then we have this ranking for different types of estimates. They could come from another model. They could be a guess, but a guess might actually be better than something that Ecopath estimates. Could be an approximate or indirect method. Could be sampling locally, low precision, or sampling locally with high precision. And as we move down this category, these categories, we associate higher and higher pedigree with it and lower confidence intervals. So it's a very structured way of addressing parameter uncertainty. And as such, it really serves the value of informing the model as we start looking at uncertainty for Monte Carlo ones. So very strongly encourage you to use this approach, and a nice spin-off of it is actually that we developed this, Danny Paul and I, back in 20 years ago. And the neat thing about here is that after all these years, I don't think anyone has questioned these confidence intervals. You can do it, and you can change them if you have better information, but the advantage of using the ones that are there is you don't have to explain them. It's just default values, and there's been some. It kind of works, you know. It's reasonable. It's the things I talked about being really important when you're working with this kind of models, that you that it makes sense what's in there, and that's the case for this. So that's and for me an argument for do this. Get this. This is a great way of getting uncertainty in. It's much better than say, oh, biomasses in this system here are estimated plus minus 40%, and PB we have plus minus 20%, and so on, and to use that across. Actually looking at this with the structured way, I was just about to say adds information, but it actually does. And that information is something you can convey. So that's the second product of this. If you just look at that table up on the lower right, red doesn't mean alarming, it just means it's kind of warmer. That's where the more energy has gone into addressing it. So you can see here, just from looking at this ecosystem here, we know quite a lot about catches. Yeah, we know quite a lot about, because they're red, we know quite a lot about the biomass of whales and seals. Well, that's because the whale watchers actually know how many whales and seals there are there. They count them. We have some information about the biomass of cod, but we have better information about the production biomass ratio for cod and whiting and mackerel and anchovy. That's because we have assessments for those. And the assessments are pretty good at estimating mortality rates. They also tell something about the biomasses, but you can see from the orange color that it's not quite as full of energy, quite as hot. And QP we know a bit less about this. So you can just from looking at this, you can see right away, oh, we don't know so much about zooplankton. So you get this picture just from looking at it, what's there. What do we know about this ecosystem? And remember, when as a modeler, ecosystem modeler, you have to get data from everything in that ecosystem. And it's not your fault, basically, if there's a lack of information. On the contrary, you can point that out, and you can evaluate with this how important it is. So we're going to be using this next for sampling. And we sample random values based on these confidence intervals. So just like with pi there, we drop them randomly. Here we sample from, for instance, from the biomass estimate, plus minus whatever confidence interval there is based on the pedigree. So this can actually be used to, is being used to inform about also what are the consequences of if we had better information. You can look at this by just changing the pedigree and say, if we had more information, what would that lead to with regards to our research question? How much better would we do with that research question from this? So they really create these, this pedigree is a pretty neat way, is a very neat way actually, of addressing what do we know about the system and what are the implications of uncertainty here. So when you define your pedigree, you can put it into Ecosim, and in the Monte Carlo routine in Ecosim, which we're going to demonstrate in not, well, today, not very long, in 15 minutes or so, 20 maybe. These Ecosim Monte Carlo routines, they can then be used to evaluate the impact of uncertainty for the Ecopath input parameters. That's what they're looking for. It calls for time series, because what we're doing is to create new models, and then we run them and we see how they work through a time series. We don't do the fitting at this point, but we can then say, okay, based on this sampling and doing thousands of runs, we're finding a combination of input parameters that's within the uncertainty that's defined for this system. And we can use this to see if we can find a better input model, a better model for input. And that's what we do with these Monte Carlo routines. And I'm just stopping here for a second to say that's one way often. But in essence, when we're doing this, we're creating a whole suite of Ecopath models. And it's also possible to save all of those balanced Ecopath models and then use each of those to address the impact on the research question that we're interested in later on. So that two different avenues. Find the best one with the Monte Carlo and use that for future analysis, or three different actually. Or save all the Ecopath models. And the third one is, of course, thing you can use this for is just to look at based on uncertainty in the Ecopath input parameters. What is the impact of that directly on the research question? With a lot of assumptions, because you can't look at all the uncertainty all the time. And those uncertainty can be, we're not varying the vulnerabilities, we're using one fitting for it, generally. So we have to narrow it down. Everyone has to do that that works with complex model. You just can't do all the uncertainty all the time. It's not even interesting. You have to be able to keep it in your head what you're doing. So that's an option here. Now I put this complex Ecopath time series fitting in here for two reasons. One was to remind us of this judgmental evaluation you see down the bottom here. This is the one that's being used to capture the garbage in, garbage out syndrome that we talked about before, and the reason why it's difficult to use an automated routine for it. Once we're past this stage here where we do not have any gross convention errors, then we can look at uncertainty up here and going through this routine here, going in and varying things in different ways. We talked something about that, we discussed this already in context of the time series fitting. So the slide is here now just to remind us about the procedure that we are using when we are working with time series fitting, which we strictly speaking which we don't do normally in when just running the Monte Carlo. And again, I want to remind you about the question of time series fitting. The question about how many parameters you search for. We talked about this earlier. Just want to mention also that this is getting quite a bit more scrutiny now. One of the outcome of some of the lectures we've had here is that we're talking, that's Jacob Bentley taking the lead on it. Dave Chagaris is involved, and Carl and I, and Sheila, and who else, but, oh, no, Natalia too. So people you've seen here, and mostly in as guest lectures, going together and putting together a paper that actually describes in more detail aspects of the time series fitting. How does it work? What does it mean? And what is good approaches for this? So that's coming. Oh, the more parameters you search for, the better the fit, the poorer predictions. Do remember that. So, on the uncertainty part, on the time series fitting part, the key there, summing it up, we talked about it before, is that there are various approaches. When you work with this in the previous assignment, I think the conclusion for many of you were that indeed searching by predator is the most efficient way of working with, as a general rule. One of the things I always do on this is to use the search group with time series. That's one of the fits that I do, and it often ends up as one that works pretty well. In many ways, it's the most efficient. Now, there can also be cases where you go in and where you use predator-prey combinations. So, for a given predator, looking at fitting for a given prey. So here, you see here, remember again, the colors here mean find one vulnerability. So in this case here, this illustrates a fit where we are fitting one vulnerability for predator 1, 1 for 2, 1 for 3, 1 for 4, and for all 9, for the first 9 we are fitting one parameter. Number 10 does no fit, it stays on the default value. We can try different things with this, but when you're using predator-prey combinations, I just wouldn't trust, I'm hesitant to trust that the sensitivity routine that you get when you go in here, you click the sensitivity of some squares to vulnerabilities, you get this pop-up screen where you can go in, you can run it, and it will show you which vulnerabilities are most sensitive to, for which vulnerabilities the sum squared residuals has most effect. It goes in and it changes the sensitivity a tiny little bit, and then it runs model and you see how much did that change in vulnerability, tiny, from 2 to 2.01 or something like that. How much result did that have? How much change did that cause on the sum squared residuals? Be that bigger or small, doesn't matter. But how big was the change? It can find the most sensitive parameters of what we're asking it to do. And it can do it by predator, or it can do it by predator-prey. So my warning there is, if you do it by predator-prey and it comes and says, oh, it's really sensitive to this and to that parameter, you really have to think about, does that make sense ecologically? Even better would be for ecological reasons, if there is a reason to think that one prey type only makes itself available to a predator under very specific conditions that somehow limits how much is possible or not, that's different, then you can test that with this. But trusting the sensitivity of sum squared, trusting this sensitivity routine to identify where that ecological makes sense, I don't think it makes much sense. Anyway, this is part of what we're talking about and we'll be talking about in this paper. And you can certainly see hear from this what my view is on that. So this time series fitting is another part of the uncertainty, and there's actually a lot of uncertainty about how best to go about it. And I think my overarching advice on that one is, let me illustrate it with how things worked out before we got the automated fit to time series constructed. When we were able to go in, we just had that you could go in and you could change vulnerability and see what that would lead to. There was there were a few papers, number of papers on manual fitting. And I saw colleagues that would very, very carefully go in, and they would sit for days or weeks and manipulate these vulnerabilities, and I can get this group to fit a little bit better if I do this, and gradually moving in and getting a vulnerability fit that was okay or great or whatever, and treating that as if it was a holy grail, as if it was, okay, I found the truth, the whole truth, and nothing but the truth kind of thing. It just doesn't work like that. What works much, much better is to go in, fit the model, look at what does it tell you about these groups. Are they close to carrying capacity? Are they far from carrying capacity? What can you learn from it? And then throw it away and start again and try again. Maybe a different combination, try different things, explore it and see what can you get to fit and what can't you get to fit. In the assignment about Anchovy Bay, the tutorial there that we had recently, there was, when you just let this out on its own and you fit it to, say, the fish species and the whales, it would increase the vulnerability for whales in order to get whales to increase, so that they would eat more prey, more predators. They would eat more prey because there are more of them, and that prey would in turn be eating shrimp. And the model really wanted shrimp to increase because catches of shrimp were going up in the time series. So it was used as an indirect method of getting more whales to get them to eat more prey, so that there'll be less predation on shrimp, and shrimp would increase, and then it would jazz up the vulnerability for shrimp in order to get shrimp to react more to this lower predation pressure. And it was all an artifact. It had absolutely nothing to do with reality in Anchovy Bay, because what was missing there was a driver. The driver for shrimp effort, shrimp trawler effort, has gone up in Anchovy Bay over the time period. That driver was missing in the time series. So in this case here, this is where we get back to the, see if I can get there. This is where we get back here, that when we should look at that model and say, oh, there is an error pattern here that we can see what's happening. We are missing a driver. And if we miss a driver, we need to do something about it. And what do we know? What can be the reasons for it? That's one reason why, major reason why I'm arguing, you don't just go in and run this and you say, okay, I got it. I got a nice fit. This is it. You really have to look at it. You have to think, does it make sense ecologically? And you get different, you get more idea about this if you run it a number of times. Look at what comes out of it. And yeah, you can do some predator-prey too. You just have to be really, really careful with them, and you have to be concerned about what happens when you use the sensitivity routine on the predator-prey. Does it really make sense ecologically? Ask those questions. Don't just run this and do it automatically. I mean, it can look very convincing when you send it off in a paper, but it also has to make sense ecologically. there is there is no correct way of doing this. You really have to work with it to figure it out. Now, one thing which I've also emphasized before is that the number of AIC data points, how many independent observations we have, is really important for this AIC. And if you haven't heard it before, I need a refresher. AIC is an information criteria called archaic information criteria. These are used, this kind of criteria, a lot for identifying the best model. Now, we are dealing here, the assumption in them is that the more independent observations you have in your data series, the more parameters you can estimate. So this is a simple equation that's based on that. How many independent observations you have is a big question. It's very few. It's not as the default when you go in here is, oh, all of the parameters are independent. So what the routine does is it calculates how many points there are in the data in the data series, and they aren't really independent. They aren't independent. That is more the rule than the exception. It's the exception that they will be independent. The rules are then they're not independent. So it's easy to compensate for this and to see how sensitive your model is to that assumption, and or rather how sensitive your choice of best model is to that, the best fit is to that, how it varies. See, in this case here, this is one where it's still actually Bay, but it's one with a lot of data. There's 164 data points, not 19 as in the assignment. This here is with the full model, all the time series and so on. There was 164 more time series, more data, and more years, or whatever it was. There is a spreadsheet I put on the tutorial page for the course about AICC calculations. And it's a very simple one where you can go in and you can take the output from this output screen here. If you run a number of different tests, drop them in there, and then you can see what are the consequences of varying this number. And when you run with it, you can actually also just see, well, what if I instead of 164 said I'm only going to use half as many, 82 or 41, and see, does that change? And then if you change this number, it will recalculate what's in here in the output, and it will update this spreadsheet that would have been here if I had run it before putting this thing on the screen. So you can use this to look which models, how sensitive it is to the assumption about number of data points. And I've seen a number of cases where, as you went down, decreased that number, you had to go really far before it changed which models were the best, or maybe you get 2 or 3 quite similar that works best. But don't just take it for granted. A sensible reviewer will question it if you have the number that you assume that the data points are independent. So you have to be you have to be careful with this. You have to think about this. You have to evaluate this. That's what it boils down to. Fair enough? So, next is, this can be tedious. You may have to do this, you try with 2, you try with 3 groups, you try to estimate for 4. And on top of this, there's also the anomaly search. You can estimate different forcing functions for how prime production has changed, environmental productivity has changed over time, primary production anomalies, we call them. And you can use a spline function that has 2 points it can vary between, or 3 points, or 4 points, and so on. So you can make more and more detailed patterns over time, the more you do, or you can do it for every year. Just estimate an environmental productivity that feeds into, for instance, prime production or phytoplankton production. So you can do all of this. There's quite a lot of combinations. This is actually a good way of saving time. What they have done from SAMS. That's the open lab where Sheila Heymans and Natalia Sarpetti used to work. So they made this routine here for stepwise fitting. It's in your EWE in the tools menu. It's a way of working your way through a lot of different fits in an automated manner. So it will go out and do all of these different, like first it would have fishing. I don't even remember what the fishing does. It has fishing, but it uses default values for all vulnerabilities, and it's enabled. Then the next one will be fishing, and it takes the most sensible predator, estimates that, and then it does a run, and it looks at what's the sum squares, what's the AICC, and so on, and what happens to the system. Next, it would do the same. It would, based on which are the two most sensitive vulnerability predators with regards to vulnerability, and we run that, and 3 and 4. So this here, there's probably just 9 groups in this ecosystem model. It sounds like Anchovy Bay, actually. It is Anchovy Bay. Anchovy Bay true. So there's one with full time series. And then it will go out and it will do just keep the fishing effort, and it will have 2 spline points for prime production, 3 spline points, and up to 9 spline points. And then it will do combinations afterwards. And this thing can go on for days. Jeroen found a way to, I think it's done that to multi-thread it. Is that right, Jeroen?
That's not in the release yet that we have. It's not in the version that we have yet. It's in the development, but I've split basically the computations up in parallel because it's just a lengthy process to run a single fit. It's not computationally intensive. So now, depending on the amount of computational cores you have in your computer, you can run a number of parallel stepwise fitting attempts, which basically reduces the time. On my machine, my development machine, it runs 16 times faster than it used to, which is kind of nice.
Yeah, and it used to be something that could, for a more complex model, take a week or something like that to run this.
Yeah, that's now a few hours.
Yeah. So something about this routine. One is it limits the number of parameters to be estimated to 1 per time series, and that's rather an arbitrary number. It may be higher, it may be lower, but it really shows or it really illustrates that we're not talking about that you can estimate 5 or 10 parameters for each time series. That would lead to overfitting. But anyway, this is one of the things that there are lots of developments happening around this, including that paper that I mentioned a little while ago, which may well result in that this some little bit more flexibility here. We may, be able to say, okay, that number can that we may be able to vary that number, for instance. But that's not really important. It's the one is if you have to assume something, 1 is a reasonable choice. It certainly is better than 5 or 10 parameters. It depends on how informative the time series are. How much contrast do we have in this time series? If they just show a group going down or up, there can be lots of explanations for that. For instance, if it goes down, you can't tell from that whether it goes down because it's fishing from a very big unproductive group, or if it's fishing. Well, anyway, you can't tell. There's not very much information in such a one-way downhill slope or build-up, compared to if you have a crash and you have a build-up. That gives you much more information about it. But yeah. So I question again this thing about AIC. How many independent observations do we have? So you can see here the outcome of it. We can go in here and it will tell us that, AIC, we're looking for the lowest number. So in this case here, minus 208. Oh, down there, minus 231. Probably minus 236 down there. So that's actually the lowest, indicating that with just one vulnerability and 6 prime production. So this indicates that it might be possible to explain what happens here through primary production. Now, this is actually probably a good example of where you would go in and this is not probably, but this is a good example of where you have to go in and you have to look at that estimated prime production anomaly and figure out, does this relate in any way to what we know about what happens in the environment? I think in this case here it goes out, and it may be going out to try to chase something, some values, and it finds, it can do that by having a more detailed primary production anomaly shape rather than doing it by vulnerabilities. So without the environmental signal, that's what we're seeing up here, when just estimating vulnerabilities, it's doing okay, but it can actually do better when we put in the environmental variability, indicating there may be a signal that propagates through the food web here. And again, these are the cases where you really have to go in and check, does it make sense what's in there? Or could it just be that the assumption in the AIC about number of independent observations, how is that impacting it? Actually, maybe not, because here it's just impacting 6, 7 parameters. Up here it was doing 6, 7, 8, 9. So there seems to be an environmental signal in here. That's probably what it points to. But again, don't just take this for granted. You have to go in and you have to look at what is it telling you. What is it telling you about carrying capacity? What's it telling you about environmental signals? Does that fit into what we know? It's this common ecological sense that ecological common sense might be the better word for it, that I am advocating. And if you're new to this, it might be daunting, but the way you develop that ecological sense is by looking and reading and seeing what happens and looking at different systems and reading more papers and thinking more about it. So experience helps a lot. All right, these just illustrates that when you run the routine, it can save a CSV file and you have all the information in there. We have a few more things, and we've been going on for an hour. I would probably prefer, though, to just take the last few slides, and then we may look at these in the program next. So here, multisim is for addressing questions that relate to time series uncertainty, environmental environmental function uncertainty as well. And there's a user guide when you run with it, what you do is you click this example here and you get a CSV file, and then you can manipulate that CSV file to get modify the time series. It can be different time series, but more commonly this is used with different environmental forcing functions or different, actually I don't know if it's more common, that's just how I've been using it, to look at what if we have different environmental functions. So for instance, I'll see an example. We'll see the example in a little while, so I'll wait for it there. What comes out of it is a suite of indicators, as you can see over here on the right, for how they are impacted by these differences in these different time series. So a short version again is you take out, you use a CSV file, and you go in and you change the numbers, and you just create a lot of different time series, and then you can get more kind of a band on the uncertainty. Oh, I thought I had a. What happened to that? I'm so sure I had a graph. Maybe it's coming a little bit later. Jeroen, do you want to talk about the EcoSampler? I talked enough.
Sure. I can explain a bit what EcoSampler is about. We wrote EcoSampler as a tool to allow to basically take the Monte Carlo results a bit further. Monte Carlo allows you to estimate, find different alternate mass balanced parameter sets for your model, and see how well those meet your time series. So how to see which set of base parameters would better approximate your time series. But that would only apply to Ecosim, and we thought, Monte Carlo does all this fantastic work. Finding alternate mass balance parameter sets wouldn't be fantastic if that could be applied to any module in Ecopath, in Ecosim, in Ecospace, and even plugins. So that's what EcoSampler does. It's a very simple tool, actually. It has basically two modes. You have first a record mode that is explained here in Willy's in the top point. So if you click EcoSampler in record mode, and you start executing your Monte Carlo runs, every time Monte Carlo finds an alternate mass balanced model, so where all E's are less than 1 and where there's no negative respiration, etc., EcoSampler will record that sample as an alternate parameter set for your model, and just keep it stored in the Ecopath database as an alternative mass balance snapshot. And as long as Monte Carlo runs and EcoSampler is recording, those samples get stored. You might think that's maybe a bit silly, but for some tightly controlled or complicated Ecopath models, and especially if you start perturbing diodes or something like that, it might take quite a while for Monte Carlo to find an alternate mass balance set. So at some point, it becomes really worthwhile to record those and keep them for later. There were models like Steve Mackinson North Sea model that Monte Carlo might find 1 out of 1,000 or 3 out of 1,000 attempts to find an alternate mass balance parameter set. So what EcoSampler allows you to do is basically capture those. It even has a facility that you can run this on different computers at the same time on the same model, amassing a total set of samples and bring those together into one master model for analysis. Well, the analysis part is then that you can replay those examples throughout Ecopath, the EWE software, and whatever model is loaded and whatever plugin is loaded. So it will fire those parameter sets off through Ecopath. If Ecosim is loaded, Ecosim will be run. If Ecospace is loaded, Ecospace will be run. And if you have plugins that run with Ecosim or Ecospace, those will run as well. And whatever component of Ecopath is set to automatically save data to disk will save as well under a specific folder for each sample. This allows you to collect an enormous amount of data based on your alternate mass balance models. That's basically what it does. We haven't put any sophisticated statistical analysis in the software to analyze all the output. For one, because the output is basically unended. Any plugin that anybody writes can respond to alternate samples. So there's no point in trying to build statistical analysis within Ecopath itself. Plus, there's much better software for that called R and MATLAB, etc. So you just basically unleash your statistical tool on this amount of output data. EcoSampler does save also the perturbed inputs with the outputs, so you can correlate the two. And it's an attempt in at least assessing parameter uncertainty on Ecopath. It does not yet take parameters of Ecosim or parameter variations in EcoSpace into account. That all could come. It's just basically a prototype of a new way of dealing with uncertainty in Ecopath. I hope that makes sense.
It does. Thank you. Oh, did we have? We have one more example.
Yeah, this is a paper by Javier Corrales where he applied EcoSampler. On the left hand here, you see what EcoSampler generates on your disk. Sample 1, sample 2, sample 3, etc. And those are basically alternate mass balance parameters. And in each folder, you see what it stores. And here, in this case, it just simply stored the Ecosim results that were turned on. It might also put EcoSpace results in here if EcoSpace is turned on, etc. So EcoSampler simply hijacks the Ecopath output path, appends a sample folder, and all the other tools follow suit by writing to those correct folders. Be careful, by the way, in the Ecopath user interface on the top bar is now, there are now two new buttons which are kind of important. There's an auto run button that tells you all the modules that are running with Ecopath. And there's an auto save button that tells you whatever is auto saving. In other words, whatever is polluting your hard disk. It's good to keep an eye on those two buttons. If the auto run button is pressed, something might be slowing down your EWE runs. If the autosave button is pressed, something will be writing to disk, which, it can add up rapidly, especially with EcoSampler and EcoSpace. If you use those together, it can go quite quick.
So when we have that kind of warning, Jeroen, we need to remember when we open EWE just to show where those autosave runs are. Okay, we'll continue. Just one more aspect of uncertainty, and this is something called management strategy evaluation. It's quite brief, and the way it's implemented, or what I'll say about it is, it's about uncertainty in the management process, how we deal with that. This is a key focus of fisheries management today, and it actually has its roots in well, I guess it's Carl Walter's Adaptive Management of Renewable Resources book from '86, where he, based on control system literature, talks about management performance as part of open loop and the closed loop. The open loop is what we're using for fisheries policy, where we're trying to find what is the best way of managing an area when there's no feedback. So we are going in and we're looking for what kind of efforts can we use to optimize certain things. We talked about that last week, I think. Now, there's no feedback there, but if there was a feedback, and that's a closed loop there, so for every year we get information back, so we might set the quota and then look at what happens to the resource based on that quota and let that develop over time. That approach there, the closed loop, is what has developed into the what's now called management procedure and management strategy evaluation. And quite briefly there, one of the things that happened was that Carl Walter's second PhD student, ADM Smith, Tony Smith from Hobart, at least that's where he worked later, Australia then, he worked on aspects of this with Carl when he was here for his PhD. And then after a while he moved, he was in London or England, he moved back to Australia, and after some years he started picking this up and really developing it. Australia has done a lot of developing the management strategy evaluation at CSIRO in Hobart. He also very smartly changed the name from closed loop analysis to management strategy evaluation, because that really is about is to look for management strategies that are robust to uncertainty. It's also it was also developed quite a lot by Butterworth's group in South Africa, where they called it management procedures, and those words are now used, one or the other or both combined. The root of it and description of how it works is actually from here. So you look at control rules and the procedures, and you evaluate the probability of actually achieving your management objectives. That's what you do with this. It looks at uncertainty in the management process. And the management process are things like impact of sampling, impact of how you set the quota and what's robust to that. And we have some approaches for that in EWE, built into EWE. I'll just illustrate the logic of it here. And this is an Anchoveta example here where I have, for fun, have turned the academics into an ivory tower over here. And in this one here, we have a full ecosystem model that knows exactly what goes on in the sea. In the management strategy evaluation, management procedure lingo, this is called an operating model. And the assumption here is that this is knows exactly what goes on in the sea. In brackets, the reason why Atlantis is called Atlantis was it was developed as an operating model for management strategy evaluation. And can you think of a better name for an operating model representing the real world than Atlantis? I think it's a neat word for that. So this is the operating model. And we can use EWE, our ecosystem model, as the operating model. Assume that it knows exactly what goes on in the ocean. It knows everything. That's what an operating model does. Now we're going to manage it from over here. So how do we best do that? What procedure can we use that doesn't mess up the ecosystem, but gives us lives up to certain objectives for how we manage it? That's what we're looking for. So we send ship out to sample, and we get a stock estimate with uncertainty for the Anchoveta. That's what we want to manage right now. So that's step one. Step two is, we also know they're impacted by the environment. So we get an estimate for what happens there, El Nino effect or so on, again with uncertainty. That's good. Based on this information, we can define what quota should be used for Anchoveta this year. So we set the quota in our ivory tower for that. The next step is it's going to be fishing. And fishing is going to be fishing a number of Anchoveta. It's also going to be fishing other parts of the ecosystem. That's fine. But right now we're concerned about the Anchoveta. Now, when it fishes, it catches an absolute precise number of fish. The operating model knows the exact precise number of fish caught. But we don't know that. So we have a catch estimate from sampling with uncertainty. Now, based on this information here, because we again look at the stock estimate and the environment, we can then evaluate a new quota. It makes a closed loop. We are closing these loops. And we can go on, and we can go on, and we can go on, and we can then evaluate different rules for management, different management procedures over time. So that's what we try to do with all of these management strategy evaluation, management procedures, and so on. We have an operating model, we have an assessment model, and we're trying to see our management procedure. We're trying to see how can we define something that's robust to uncertainty in the environment, uncertainty in the biomasses, uncertainty. That's what we're looking for with this. The management procedures, we can have different objectives. So for instance, what's the risk? We want a risk of less than 10% for the biomass going below 50% of B0, it should say here. We want to have as little variability in catches from year to year, would be another thing that we would have as management objectives. And then we can look at the decision rules for quota or exploitation rates and look then at how uncertain are they. It can have various house control rule shapes, and we can evaluate how good they are, how they behave based on this uncertainty. And this is implemented then two ways in Ecosim and EWE. There is a rather simple module here where you can define the harvest rule, a number of other things such as how uncertain the information is. So that's one way of doing it. Then there is a much more complex routine. They are called the CFAS MSE. In bracket, there are a few issues with those in the current version. If you want to work with this, you should talk to Jeroen or me first, and we'll bring you up to date on what's happening with this. The key here is that this is a very, very powerful routine, and I'm going to talk a little bit more about this, and I don't think we won't have time today to illustrate that. If you are interested, then talk to us. That's outside of class here. I want to highlight this paper here, which is a really, really neat paper. It's in our collection. Steve Mackinson, while he was at CFAS, took the lead on this. It was as part of this, they developed this CFAS plugin for MSE. And so they use it for North Sea as part of the management process there, where they set up a system where an interesting thing was that they created possible EWE models. So they didn't just do it with one model, but they actually set up a routine that would estimate, just like for the Monte Carlo before, it would make different models, same as for that, and it would just store these models as Jeroen was talking about we could do, and then run different models through this management strategy evaluation process. It was a pretty fairly complex procedure for how it worked. I'll stay out of, I won't go into details about that here, just mention that well-defined, structured way based on multiple Ecopath models to look at this uncertainty process. Now, choke species are a really important aspect of the no discarding policy of the EU, as we talked about before. So you may have, there are a number of these different choke species. That's just to keep that in mind when we look at the results from this. So in this case here, they evaluated 9 different approaches for how to handle this. And if we look at conservation risks for skates, then there were some policies here that had a very high risk for getting low biomass of one of the species that they were concerned about. Now, there was also a risk for the fleets. The risk is of poor economics. So when they looked at it, they found that this risk was biggest with the policies that had no conservation risk. So based on conservation here, you would say, oh, let's choose one of these for here on the right side. But when you look at it from the fisher's point of view, that's the ones that leads to low effort. So there were lots of closures when this happened. So in this case here, when you're just looking at these, you get into fisheries versus conservation. Maybe it's some intermediate here that looks better. But this is the kind of things that comes out of this. It makes the risk clearer. So in this study here, how you implement this has big impact. How you implement this guard ban has big impact for commercial fish species and for the livelihood of people. So the main thing is it makes this clear. It makes it in a very you can analyze it. That's to me is the main outcome of this, and come up with some rather clear recommendations of are implications of what the different rules, what they entail. Last thing, an hour and 20 minutes. It was not 40 minutes. I'm really poor at estimating this. No, I know it would take longer. Just mention one thing for Ecospace, and I'll do it very briefly because in next Thursday a week we will be hear much more about this in detail from Vaso Capuzzi from Hemera, who will be talking in it. But for one aspect of this, we'll probably not be talking about, is that we set up a Monte Carlo approach for Ecospace to use for this environmental impact assessment of Roberts Bank, ran it many times, 5,000 runs for this spatial model or more. So there is a procedure for that. We've implemented via plugin that can be used. Here we looked at very specific question was how does the model structure and how it's parameterized impacts the prediction about the ecological impact of a proposed container terminal. Placing 2 square kilometer of terminal out in a major salmon estuary is what we looked at here. You'll hear more about this later. So what we looked at for a number of different species was, first we made a key run. That was one well-defined run. That's the green one you see on these. And then we did all the Monte Carlo, and we looked then at the ratio between project and without project. So for forage fish, we found, say, around a 2% decline in forage fish productivity for the area. So how much production could be supported by this? And you see the range of all the thousands of runs here. And generally, there's very little variation in impact of this. So uncertainty wasn't that great in this. Number of reasons for that, but the main purpose for showing this is just to mention that, yeah, we can actually look at spatial uncertainty. There's a whole page conclusions here. In the interest of time, I won't talk about that. Just mention that Jeroen is working on fitting spatial temporal data. There are things happening around that that leads to capabilities and explanations for how to go about it. Jeroen, will you be talking about that on Thursday? I don't quite remember.
It was not the plan. I think it's a little bit beyond the scope. I mean, it's part of my thesis. I think this is quite far ahead of what we're discussing, but it basically comes to that how we can use spatial temporal models better for policy advice, and how we, because of many things you've been saying now and what has been said in the past, is that ecosystem models have so many parameters, comprehensive uncertainty assessments cannot be performed, but how, as a modeler with simple tools, we don't have access to huge clusters, and computing hours are expensive on clusters. How can you perform serious assessments of even the most suspect parameters in terms of uncertainty? How can we need tools in order to better understand our own models and why they behave the way they do, especially over space and time. And I'm trying to find solutions for that. Technical solutions that allow you to deploy stats and other things on top in order to better understand why our models behave the way they do. That's probably as much as you should say about it now.
Yeah, there are things happening on this. That's the main message for now. I have 4 slides left. Should I finish them, Santiago? Or should we go to the...
Oh, finish, and then we'll go to tutorials.
Yeah, we talk too much. There's too much stuff to talk about here. There is uncertainty. And we recognize that. Everyone should recognize that uncertainty. and our models are not going to be perfect. So the key question that we are addressing is, if we can use these models to order policy choices. Policy choices is often we're looking at. It can be science related, but often it's more, increasingly it's policy choices related to management. So some of the things that we're looking for is evaluating when we evaluate a model is, can it reproduce the way the system has responded to what has happened in the past? That may be fishing, it might be other aspects. So can the model do that? That's one, just about do a check mark, but that's one thing. How does the model behave with this? It's a question of building trust in models, not faith. As I said many times before, models are not like religion, and you shouldn't believe in them. And you can have more than one, but there are some clear distinctions there. Can it reproduce spatial patterns over locations without differences, similar to those that policies will cause? So spatial challenges, temporal challenges and spatial challenges. Can the model replicate these things? And how is it when we come to making extrapolations to new circumstances? Highlighting, again reminding you of the cultivation dispensation effects, but the extrapolations, how does the model behave? So all of this here is actually something to do with our faith in the model. I'm wondering why I put, can the model correctly order policy choices? That comes in a bit later. Weird. I should have seen that. How good are the model predictions? Again, reminding you of the vampires in the basement. And yes, there are these limitations. We have to live with them. And because of this, we are looking for how robust the model's predictions are to the things that we care about. So that's what does the model correctly order policy choices? That's what this is about. How can we test the models? All models will fail, and when they fail, that's usually when we learn a lot from them. We can't predict every possible policy choice. That's why experimental management approaches, that's what the whole adaptive management concept is about. That's why that's really important. It may well be that the only way out to explore certain questions is by doing an experiment and try it, that we can't do it otherwise. But then the modeling can be used to direct what is a sensible way of doing that, what's the optimal, or what's a good way of doing that. And that comes again from that a good model is one that correctly orders a set of policy choices. What is likely to be a better way of doing it than another way when we have to choose between. It can rule out that some methods simply aren't useful, can't likely to lead to a good result. So that implications of that in the CFAS study of Steve Magnuson just before talking about the management strategy evaluation. So that's lead us then to the approaches combining ecosystem modeling and adaptive management. Key there is develop alternative models. Look at environmental versus fisheries versus food web effects. That's what I talked about ages ago. Class 19 minus 18, the very first class we had here, I was talking about one of the lessons we've learned is that in order to understand what happens in the ecosystem, you have to evaluate what happens in the food web, the trophic effects, versus the environmental versus the fisheries, that combination of effects from all three. We very often find that if a question has a straightforward answer, such as fisheries caused this species to collapse, or high temperatures caused lack of recruitment for these species, when there isn't that kind of clear impact, it's often a combination, and we're seeing that all three effects are important. So when that happens, you can develop alternative models to look at this, And you can also develop management experience. Could be spatial closures, other changes to modifications, to the habitats, keeping predators out, number of different things. Read much more about it in Carl Walter's Adaptive Management book. I was going to show you something about how we run the Monte Carlo. We're going to combine that with using the EcoSampler. Now we are at it. Let's grab a model. Anchovy Bay, you heard about before. We're going to go to Ecosim, load a scenario. If you are trying this on, when you're trying this on your own, don't worry about what version it is or so on. It doesn't really matter for this. And because we're going to do Monte Carlo, we'll need time series. So I just use these drop-down menus where Ecosim, the clock here, has scenarios above the line and time series that are stored in the database below. And we have one called Anchovy Bay Annual. And once we have done that, my next step is to go run Ecosim. So Ecosim output, run Ecosim, and do a run. So here we're doing a 40-year run, roughly, and we see that what the model is doing from this. And again here, the lines indicate Ecosim run, and the dots indicate that here we have seals increasing, and that's how much they increase here. I have a sense that vulnerability have been estimated here, so we are estimating here. It's estimating a very high seal vulnerability, a very high whiting vulnerability, and a low cod vulnerability. So the assumption here is that with the fishing pressure, it needed a lower vulnerability for cod, not to crash it. It needed a higher for whiting to make it go down enough so they could indicate an exploitation of whiting before the model was run. And then the higher one for high vulnerability for seal indicates that the culling that had happened in the decades or centuries before the model was started had moved seals very far from carrying capacity, and that makes them actually, a symptom of that when running the model is that that's what makes seal increase more. So here they're still not increasing enough. So even with that high vulnerability, we cannot explain the full increase in seals, which immediately should bring us back to, oh, what are we missing here? Environment, maybe? But that's not where we're going now. We're going to go, and based on what we have here, we're going to go and we could address it here. We're going to go and we're going to do some Monte Carlo. So this is under Ecosim tools. There's input, there's tools many places. That can be a little bit confusing. There's also an output tools, but there's this overall tools where you find a number of different tools. Of these, by the way, the FMSY and the fishing policy search, we have 2 previous tutorials about this, which we haven't done, but and we've had some problems here with my screen sharing, so we haven't recorded them, but we will record them and put them on YouTube in this week. Right now we will just have a look at the Monte Carlo simulation. I'll first introduce this and then we'll talk about the EcoSampler next. So when you could get into the Monte Carlo run here, first of all, you need to have time series loaded for this. I think you might even be able to choose them here. Here you set how many times you want Monte Carlo to run. When you're doing this in earnest, reviewers like round numbers, 1,000, 5,000, 10,000, that kind of numbers. So that's what you set here, but for our demo, 20 is fine. Then settings first. What do we want Monte Carlo to be able to vary here? And for those, and a newer thing there is that it can vary the diets, and in doing so, that's a little bit time consuming. It makes do many trials in order to do it. You can also retain better fitting estimates. You don't need to do that now, but that basically is one where you store the best fitting one, and it will you can load that and continue with that one later. Or you can use the EcoSampler, which we'll get to in just a few minutes. Can do the same. So that's what we're doing settings here. Now here on the biomass, you can load the biomass CV from Pedigree, which is a good way of doing it for anything serious. Or you can go in and you can do this quick one here of changing the CV. It leads to your mean value is your biomass input in Ecopath, and then the lower and the upper are calculated based on this variation here. Again, you can go in and you can change this to whatever you like. You can even enter your own numbers and so on. So it's very flexible. You can do this for whatever you say here you want to do it for. They will show up here. So biomass PB, QB, you can see which one you can change here. EE, the same, that's only EE is input for one group, so that's all you can do. Biomass accumulation and so on. What you have to think about is that when you're sampling from here, let's say the chance that Ecopath will fit when the biomass is vary this much for when you sample it, will it fit the model with this variation? We sample something from this range. Let's be really optimistic and say there's 99% chance that it will fit. So that means if you just change one, there's going to be 99% chance of it fitting. If you fit two, there's going to be 0.99 raised to a factor of 2. 0.99 times 0.99. Still a lot. But you have to do that 10 times here, and 10 times here, and 10 times here, and one more here. So you can see what is 0.99 raised to 30. It's getting into a pretty small number for it to fit. And if it's not 0.99, if it's only 0.95% chance, you can see why it may take a lot of runs to do this. I'm just going to run the trials, and then we're going to load the EcoSampler and see what happens. So now we go to biomass plot here, and we're doing 20 runs. And you can see up on the right here that the original sum squared residuals were 4.4, and they found one of 3.49 as the best out of 20. On the average, it has to do 12 runs in order to find a balanced model. And we've done 14 now. You can see, no, sorry, yeah, on the average it's 17. No, that number is wrong.
So you know really how this
The calculation of this is wrong. You can see here how many it is. They were all above. Yeah, so that's a little hiccup in that calculation. It doesn't matter. It's not being used for anything. It's just to entertain you while this is running. But generally, it used something like quite a number more. So you can get here. Oh, see, there are a few cases where it could get whales to increase quite a lot by changing these initial parameters somehow. Interesting. Let's try it again.
Really?
Yeah.
How it works is that you ask Monte Carlo to do 20 trials. For every trial, it will try to resample the Ecopath parameter set for the variables you indicated 10,000 times, which is basically what it calls the Ecopath runs here. And you can see that numbers 16, 21, 18 was the amount of times it had to resample the whole parameter set in order to find a balanced model. It may just very well be that some trials will not produce a balanced Ecopath model if you tightly constrain. So there's no guarantee that every trial will produce a result.
No. Yeah, okay. I just had the impression that this average runs here was a bit on the low side, but not sure. Okay. We've done 20 trials. We can get from this, we still have a couple that really takes off here and kind of obscures the plot. So, you could zoom in here. Not that it serves much purpose, but certainly not for me right now. Unzoom all. Back again. So Jeroen, the next thing is to go to Tools. Will you walk us through it?
Sure.
So this is the Tools. There is
the tools everywhere.
Ecosim, Ecopath, Ecosim, there's EcoSpace, and they all have tools, but then there is a final one down here called Tools.
Overarching tools. We thought this was a good idea, but maybe it isn't. Anyway, there's EcoSampler. So if you click EcoSampler,
we could actually have had all the tools together and have Ecopath, Ecosim, Ecospace, and then doesn't matter.
No.
It's somewhere. And it's actually great to move around the navigator and familiarize yourself with what's in there. So what do we want to do?
So why don't you throw EcoSampler up in the air?
Click EcoSampler.
Yeah. So EcoSampler opens up as a panel on the side because the data it contains is quite limited. Here in EcoSampler you can click the record button. You see it on the top. And that puts EcoSampler in record mode. You've already have quite a lot of samples here. I think your screen resolution is such that we cannot see the scroll bar beside the panel. You can scroll up or down. Okay, good. So you have about 27 samples here. And they were all created on this computer yesterday. So if you now start Monte Carlo, you'll see what starts happening. Yeah, it remembers what computer they came from. This is one of those features that was built to, in order to collect samples from different computers. You can import them from other machines. See, there's the import button on top. So you can run Monte Carlo. You can collect samples on different computers, especially on tightly constrained models, or models that are complex. If you want to resample a diet matrix, for instance, you can copy a model to different computers, run Monte Carlo an immense amount of times, have an EcoSampler record, and then use this import function to bring all the samples back into one model on which you can do an analysis. So if you run Monte Carlo now, you'll see that it will start recording trials. It's ticking over. The scroll bar repositions itself, but so the parameter sets that Monte Carlo is now producing are intercepted by EcoSampler and are stored in the model database.
Oh, now we're starting to get this whale increase again, yeah. So you can also see from this, by the way, the thing we talked about, that like the green here for COD, so that would be 20 different runs to evaluate the impact of uncertainty on COD under these conditions here.
Okay.
So over here we now have that many runs.
Yeah, you produced 20 more. Then update to latest SS. Oh well, fine. So now you turn record off. You probably don't want to do this again, unless that's what the session is about. So these samples are now stored. You can select an individual sample and load it, and explore it in the interface, run it through Ecosim, run it through Ecopath, etc., and explore how it works. And if you want, you can delete even individual samples. So there's a load button.
So I click this one here, and I can load it.
Yeah, and
now, and I just mentioned that you can see now I can't save this as such.
you don't want to save this over your initial parameters. That's not a great idea.
No.
You can only discard the sample if you're not happy with it. But now you can go to basic inputs, to your diets, you can explore, you can run Ecopath, you can see how the sample behaves. And then you can unload it again to revert back to your original state.
So we go and we can have a look here at
Ecopath basic inputs.
So now they have been changed from what they were. We can go run Ecosim.
You can see
it's
how
going to be interesting to run that here.
Well, EcoSampler doesn't care. Just grays
No,
over.
it's just a plot. Oh, see, it has this one. This is one that has a really nice fit to whales up there. No, to seals. To seals.
Yeah. So now in EcoSampler, if you cannot modify the model. If you do, it will restore them. EcoSampler tries to manage the traffic. When you start modifying your variables in the Ecopath Ecosim, it will unload the sample. So why don't you, for safety's sake, just press unload in EcoSampler just to stop looking at this sample and go back to the original state. Okay, the screen's reset. So now there's this batch run option in if you paid attention, you'll notice that the variables have changed. So now there's this batch run option that can fire off a number of samples through Ecopath with Ecosim. You could randomly select a number. You could say what sample to start at and how many to run. Of course, this is not really useful if you don't autosave data, because the purpose of this is to collect data to analyze later in statistical software. So there is this autosave button and the autorun button on top. Those are very, very, very important. So if you click the autosave, why don't you? Please. That's autorun. That's also okay.
Oh, it's okay.
No, that doesn't matter. This is fine. We can start with this one too. So these are the different plugins that are enabled in Ecopath with Ecosim. I'll speak more about plugins on Thursday. These are additional analytical tools that, beyond Ecopath's Ecosim and Ecospace, that just do extra work. That intercept the results from the models and use them for further calculations. And for instance, you can here turn on ecological indicators to run for Ecopath. Fine. And Ecosim. You go.
And it can really slow your computer down.
If you now say OK. Now notice that autorun button at the top is checked. It's highlighted, right? You see that there's a little blue triangle around it on Willy's computer. The button that you just pressed. That is an important button. We added that because we totally got confused when Marta's computer was behaving like absolutely abysmally. But that's because of this. So now EcoInt is running, but it isn't doing anything yet. There, beside it, Willy, if you can press the autosave button, notice that both these buttons take you to options within the options menu. The autosave right beside it there, yeah, good, yeah. So this tells you what tools are automatically writing information to disk in whatever format is available. So there's quite a lot of information that can be written, and plugins as well nest themselves here. So you can decide, for instance, you can say in the ecological indicators in Monte Carlo trial results, fine. I think ecological indicators is further down. I don't know, this is an older version. Yeah, here, ecological indicators is just a catch-all for everything. So now, if you now were to run, good. Okay, so look at your setup. You only have Ecopath loaded and Ecosim as well. If you now run your batch run, say for 5 samples, just do a few just for demonstration's sake, and we randomly select them. Okay, just to make sure, because you're going to do something that might take a while. We cannot see a status bar on the screen, which is a bit unfortunate because that tells you how far EcoSampler has progressed.
Yeah, I can't see it either. Oh, there it comes. Now it comes.
Okay, good. So now EcoSampler is chugging away, loading a sample in Ecopath and running Ecopath, running Ecosim, and whatever is connected will run as well. Whatever is set to autosave will save as well. And you see it's now, it's happily working. It randomly selects. It tells you here what samples have been selected. Okay, and the batch run is completed. Now you can now click those links in the status panel are highlighted, which means they're underlined, which means you can select them. Will you go back to the status panel? Yeah, just click one, just for argument's sake. Please. Good. This opens up Windows Explorer to the sample folder. So this is what EcoSampler produced. You have the biodiversity indicators for Ecopath that are being saved, and Ecosim indicators have been saved. Well, that's indeed what you are asked to do.
Right.
So this is indeed what you asked it to do. These are the indicators for Ecosim and the indicators for Ecopath. That's what was auto-saving for all these samples. And if you click the Anchovy Bay 2 folder, go up one more in your directory structure. Back up one. So this is the information of EcoSampler. So it tells you what the sample baseline was. So what are the baseline variables? It tells you what how things were resampled and the indicators had to go with it. In this case, right?
Yeah. Generally, one thing I find very useful, because you often have to save, is just that when you go in here to the autosave button or whatever it's called, you can find out where things are being saved just by finding these folders, and you get back in there again. That is something I use a lot.
Yes.
And of course, one thing you will see with this is there's so much output that's possible from here and from lots of other things we do. And what it calls for to analyze that this is really something using routines like R to work with this. It can be done in Excel, but it's tedious to get into all these files. Whereas setting up structure in R is so much easier.
One of the things we've been discussing is to have a repository of R scripts that people have written to analyze this data. Yeah. So have data for EcoInt, have data for Monte Carlo output. Have scripts that analyze the various outputs. It would be fantastic to start it now for once and for real. It's been an idea for a long time in the making.
It's been an idea also because we have lots of people have plots, routines, and other things. It's impossible to do everything in the interface. It's so much more powerful to have routines that will go in, read the data files, and do the plotting.
Well, and as well, in Ecopath, we draw the line. We do things that we're good at, but there's much more better statistical software out there than we could ever write. So why try to emulate that? So in that sense, a library of those kind of scripts would make perfect sense.
Yeah. We are relying on the interface, very much so, because for understanding the model, the things you can learn from going in and exploring plots of this kind really beats if it was files that you might never look at. Here, it's there, it's in your eye, in your face. You have the option, almost the obligation, when you're working with models, to go in and check what's happening here. So that's the EcoSampler used along with Monte Carlo. It all closed down here. I think that may do for a start here. Then there were a couple of things more. Are there any questions about this? And now is a good time.
There's a bunch of questions in the chat. Maybe, well, let's see.
Oh, it's 10:56. My. Oh, yep. We spent the 2 hours. Jeroen, you talk too much. There is the material on the website for the other aspects. I was going to mention the multisim, which is a way of changing time series. There is a description of it on the tutorial page. I encourage you to read that. There's also something there about the CFAS results extractor. And there is the spreadsheet for how you can go in and you can, when you have done a number of time series, you can copy the table with those time series run into the spreadsheet, and you can evaluate the impact of different assumptions about number of observers. I will invite you to explore that on your own and ask questions later on. Fully realizing that we are at class 19 and later on gets smaller and smaller. We're getting closer to the end. So, questions?
I had a fundamental question about using maximum likelihood rather than sum of squares, but I'm sure this is something you guys have thought about for a long time, and I think this is a conversation maybe for another time. A direct question I did have watching this is whether or not you'd want to run kind of a circular optimization where you go back and forth between fitting vulnerabilities and then fitting the basic input Ecopath parameters and then refitting, going about that way. Is that maybe a best practice?
It's a good practice with the clause that be careful you don't go searching for the, can I call it the holy grail again? By which I mean you go searching for something you have in your mind, I'm going to do this, I'm going to do that, and I'll take all these steps, and you lost track of how you got there. So how does that relate? How many steps did you have to take? How far did you move? It's something you have to be aware of at least. Because you can't go out and search for all the input parameters and then do all the time series fitting. It's not very practical.
Is it more about tweaking than using it to build your own model?
I'm sorry, tweaking what, sorry?
Is it maybe better to tweak the model to make small changes, or relatively small changes, than it is to...
I don't know. I don't know if there really is. There's no one way of doing it. The criteria to look for when you're doing this kind of manipulations is, can you explain it in a few sentences what you're doing? If it takes you a page to describe the approach that you've taken, it's too complicated. If you could do something and express it, it's much more likely to be passing. Let me take the criteria passing review, which that's not really a good argument, and yet it is a good argument that if you can explain it, then it has a good chance of actually being understood for other people, and that's important. And there's also much better chance that you'll understand it yourself. So I think that it's valid. I like that principle. If you can explain it, then yeah, it's probably a good approach. Yeah. And explain it. That's again, we're back into the ecological common sense. Is this something that's reasonable to do, this way of doing it? Because there is no one way of getting from A to B in the complex ecosystem. At least not from A to Z. You can't do that without picking a route through it. It's not a good answer, but I'm not sure there is a good answer. But yeah, the approaches there, Monte Carlo, the time series, they address doing specific things, and combinations may well be required. Some of this could be automated, and we're getting further and further with that. EcoSampler is a big step on that way, making things more comprehensive somehow, just like the CFAS MSE routine. By having all these models, by EcoSampler having all these models that you can analyze for, opens up for a lot of flexibility. A key aspect here is, by the way, that The interface gives you a lot of possibilities for exploring the model, what's in the model, how can you work with that, but it does not, it poses some limits on that as well. And it's great for that first step of getting to know what you can do. When you want to take the next step, that is, you want to do your analysis your way, that calls for batch runs, that calls for doing things where you don't look at the interface because you want to do that 1,000 times in order to get the uncertainty that's underlying it, to really look at the options. That's when you don't want to use the interface. That's when you want to use a plugin or a programming approach. And that is our seg for Thursday. Is that correct, Jeroen? That's what you'll be talking about.
Exactly. Yeah.
And
Oh,
with that,
before you go to run away, Holden had another nice suggestion. He said, well, instead of looking at the sum of squares when you analyze your model results, could you use machine learning? And I think there is a lot that could be done on, for instance, the results of EcoSampler to see whether there's a beeping noise. Philly, can you mute your microphone for a sec? I think it's there's some feedback. Okay, that's good. Well, could you use machine learning to analyze, digest this insane amounts of data? And you probably would need to go there, either Bayesian statistics or something smarter, to infer from your massive parameter set whether ecological realism is still there, whether this is something that's plausible. I mean, the model can produce results, but are they in any sense realistic? For instance, I don't know to what degree we spoke about pre-bal by Jason Link, but those kind of views on your data are necessary besides looking at AICs and SSs. And a combination of approaches is what this calls for.
The auto mass balance routine was made by, is an example of something that in 2003 would be machine learning. It was made by a programmer from the .com times who retired in her 30s after this big .com boom. And made a really intelligent routine, which again, you can get via machine learning, but you also have to be sure that the ecological ground steps are taken first. So you could probably get much further with this now. All right, we'll hear more on Thursday about plugins and programming aspects. And it's actually something that is quite feasible. So if you have tasks that go beyond what you can do with the interface, or it would be way too tedious to do it in the interface, it is actually quite feasible to do that with the plugins. Jeroen will talk much more about that on Thursday. So with this, I'll close this class. Thank you for coming.